Hello, I'm Toby Fisher.
And I'm Sourav Garg.
We're going to talk about our paper, Where's Your Place? Visual Place Recognition, that we've done at the Queensland University of Technology within the Centre for Robotics. This is joint work with Michael Milford. Stephanie Laurie previously defined visual place recognition as, given an image of a place, can a human, animal, or robot decide whether or not this image is of a place it has already seen? So you can immediately see how such a localization ability is crucial for embodied agents like robots or augmented agents like augmented reality devices, so that these agents can understand their operating environment and intelligently navigate in this environment and interact with the environment. This definition of a place considered only the positional coordinates, but not the orientation. However, as seen in this example down in the bottom left, being at the same physical location but facing opposite viewpoints, for example, leads to a completely different appearance, which without prior knowledge is impossible to solve for a place recognition system. We instead propose to define place recognition based on the visual overlap between two observations. In short, we define place recognition as the ability to recognize one's location based on the reference and query observations from overlapping field of views. For those of you with some knowledge in neuroscience, this is similar to the difference between place cells, like in the left figure, and spatial viewpoint cells. Place cells fire regardless of the orientation at a particular physical location, while spatial viewpoint cells fire regardless of the physical location, as long as a particular point is being looked at. One of the first applications of place recognition was in finding loop closures in a SLAM system. Indeed, as shown in the video, place recognition can be used to build a pure topological SLAM system. You can see how imprecise odometry information is corrected using place matches provided by the place recognition system. In the paper, we emphasize how the downstream task has a significant impact upon the requirements of the place recognition system. Indeed, if loop closures are proposed and no subsequent filtering is performed, the place recognition system should operate at 100% precision, as otherwise catastrophic data associations are introduced. On the other hand, if the aim is to find candidate images, high recall is required regardless of the precision. In the second video, we see the 6th degree of freedom localization task, where very tight error tolerances are needed. We identified two further drivers of place recognition research, the environment and the agent or robotic platform. When place recognition methods are applied in a robotics context, one has to pay particular attention to the computational and storage requirements. For large reference match, each reference place should be quite low dimensional to allow for real-time processing. Commonly, a hierarchical approach is used for this, where the first stage selects candidate images and subsequent stages re-rank these candidate images. The agent and the environment are often tightly coupled and can have varying requirements on the place recognition method. Aerial vehicles will face very different challenges compared to autonomous cars, and those will lead to potentially very different place recognition methods. Similarly, the viewpoint and appearance changes will vary significantly for the different environments. The demands on the place recognition system can be reduced by choosing a sensor that is well suited for the agent and environment. In this example, we show footage collected with an event camera, which are bio-inspired sensors that capture changes in the scene. They're well suited when high dynamic ranges are required, such as when exiting a tunnel. Another way to reduce demands on place recognition systems is to use odometry information, which is available in virtually any robotic system. However, many VPR systems, even those aimed at robotic systems, most commonly limit themselves to use only visual information and don't make use of additional information such as odometry or even in some cases GPS information to get it prior. I will now hand over to Sourav, who will talk about areas that are related to place recognition.
Visual place recognition problem is typically cast as an image retrieval problem. In general, for image retrieval, the similarity criterion can be anything. For example, finding similar drawings or finding images of an animal category, as shown here on the left-hand side. With place recognition, the notion of similarity is defined based on the static physical content of what is being viewed. Moreover, with general image retrieval, environmental condition types such as night or snow can be a similarity criterion. But for place recognition, we aim for condition invariant place representation and matching, as shown here on the right-hand side, where different images from the same place have been captured under different environmental conditions. Furthermore, in the context of visual place recognition for robotics, it is not just the static images we are interested in. VPR can in fact be cast as a video retrieval problem, as visual information is accrued over time as the robots move through their environment. And there is increasingly more amount of work being done in this space. For example, SIGNET, delta descriptors, or multi-view place recognition. So these are the different methods which have been developed to retrieve representations based out of a sequence of images. Visual place recognition is also closely related to landmark recognition and retrieval. So both the tasks aim to recognize unique places, with landmark recognition dealing with specific places which typically have names, such as Big Ben in London. This is opposed to recognizing general place categories, such as a clock tower. On the other hand, with visual place recognition, the aim is to uniquely recognize any ordinary place which may or may not have proper name semantics. So if we recall the VPR definition we discussed in the beginning of this presentation, we argued that visual overlap is a must for recognizing places. However, obtaining ground truth based on this criterion is non-trivial, and this in turn affects the learning-based systems. Recent studies aimed at visual overlap detection thus become quite relevant for visual place recognition, as overlap measures can be used to accordingly supervise representation learning techniques.
I will now talk about evaluation of place recognition systems, in particular metrics and datasets. Let me start with datasets. It might be obvious, but when evaluating a place recognition method, one should choose datasets that are close to the deployment setups. Here are two examples of commonly used datasets. On the left is the 17 places indoor dataset, which is very different from the mapillary street level sequences dataset on the right. The scenes differ significantly, and so do the requirements to the place recognition method. The aims of a typical place recognition system is often stated to be robustness against both viewpoint and appearance change. However, many datasets only cover either viewpoint or appearance change, so finding the right mix is crucial. One other thing that we'd like to highlight is that a particular method doesn't necessarily need to excel in all different scenarios. Autonomous cars, for example, don't operate in office environments, or at least they shouldn't. Finally, we also like to mention that the training data of a method matters. It is well known in the machine learning and deep learning community that the training and test data should be as close as possible. So when proposing a new method, one should ensure a fair comparison by separating architectural changes from training data changes, which is often not the case. Indeed, some progress has been made in these directions. The recent place recognition bench paper allows for an easy comparison to other techniques and aims to separate out robustness to viewpoint and appearance changes. VPR bench contains a range of datasets and comparison methods, and we hope that it will get adopted by the community. One of the drawbacks of VPR bench is that it doesn't contain a holdout test set. This is opposed to the mapillary dataset, which contains a difficult holdout test set for challenges, which is not yet saturated, unlike some other datasets where near-perfect performance is achieved by multiple place recognition methods. The mapillary dataset also contains a range of subtasks like day to night or all to new, where the older references images are taken several years ago and significant structural changes might have occurred in the meantime. In the paper, we also extensively discussed the various metrics that are used in the place recognition literature. Most of these metrics have their origin in the information retrieval measures, precision, and recall, as visualized on the right. The evaluation metrics are also tightly coupled to the downstream task, and we detail advantages and disadvantages of the various metrics in the paper. In this example here, we see a traditional precision recall curve on the left. Each curve in the plot corresponds to one particular method. The curve on the right complements the precision recall curve by varying the ground truth tolerance, which is fixed in a precision recall curve. An open question is how sequence matches that are very common in robotic applications to improve performance should be evaluated. Traditional metrics include the maximum open loop distance traveled, so how long does the robot travel based purely on odometry without loop closure. We think that it would be beneficial to investigate metrics that couple single image and sequence-based place recognition, I would love to hear from the IJCAI community whether you have any suggestions on how to achieve that based on similarities with the other research fields. I will now hand again to Sourav, who's going to talk about open research problems.
One of the most common ways of representing places is to form a compact global image descriptor. However, depending on the underlying methodology, the characteristics of such a representation can vary. For example, a viewpoint equivariant feature aggregation strategy, as shown here on the left-hand side as NECVLAD, it can struggle under strong appearance variations. Whereas a viewpoint aligned descriptor, for example, HOG, histogram of oriented gradients, or patch normalized images, these are viewpoint aligned, but this kind of viewpoint aligned matching can only deal with small baseline place recognition problem. And these methods can struggle if there is a wide viewpoint change. Thus, it is important to consider representation techniques that can better leverage the scene structure, especially considering general robotic application scenarios. For example, use of local structure in the form of vertical blocks, also known as stixels, as shown here on the left-hand side, or semantic blobs or objects, or even superpixels. It can potentially lead to improved global place representations. Global place representations are typically high-dimensional, which becomes a bottleneck for resource-constrained robotic applications. While methods like PCA, like principal component analysis, or quantization or binarization help in this regard, they are typically used as a post-processing step on top of learned representations. Such efficiency-inducing processes can potentially be learned specifically for the task of visual place recognition. And that too, along with the added sources of information, such as sequences or odometry. So it remains an open research problem to come up with new methods which employ all this information and still be more efficient. For visual place recognition and localization, the map information is available beforehand. These maps can be enriched with detailed hierarchical information, such as that presented in 3D dynamic scene graphs, as shown here on the left-hand side. This can improve localization abilities, particularly at large scales. Also, these maps can be curated to uniquely and robustly recognize places. For example, either by identifying relevant visual cues or by appropriately selecting images from multiple runs of the environment. Thus, it remains an open challenge to define and design ideal map representations. To deal with the viewpoint changes, view synthesis has also been explored in the past for visual place recognition. However, automatically generating accurate novel views is challenging. But with the recent advances in the field of neural radiance fields or nerves, the relevance of view synthesis for place recognition can be revisited. Apart from the task of representation, the matching method is also equally important. While a hierarchical place recognition or localization pipeline is a common setting, developing mutually informed hierarchical systems is an open research problem, where the complementarity and information flow between different types of methods or hierarchy levels needs to be better studied. So there already exist methods like multi-process fusion or local plus global features which are learned together, or better informed global to local information transfer. But there's still a lot to be done. Researchers have used a range of distance or similarity measures for the task of place matching. The suitability of particular metric to different representation types is not well understood. Furthermore, learning to match frameworks have been explored in the literature and could potentially be a better solution, but they often lead to additional computational overhead. Thus, more research needs to be done in this direction. VPR research to date has broadly addressed the problems of representing, associating, and searching using spatial data, and is one of the key enablers of spatial AI. Further advances in VPR research will require unifying the efforts of computer vision, machine learning, and robotics communities for the autonomous embodied agents through spatial AI to become a reality. Many thanks for listening to our presentation. It would be great if you get in touch to hear your feedback. Thank you.